Hello everyone, we are the WWVB receiver group. I'm Yi Dongfang.
My name is Zhitong Fan.
My name is Zerui Li.
Our project is a part of the VLSI Design Lab, taught and supervised by Professor Peter Kingett and sponsored by the Apple Incorporated for the fabrication. In this video, we will give you a brief introduction of our WWVB receiver IC design. Let's move to our slides.
So, what is a WWVB? WWVB has a transmitter located at Colorado. It can transmit some signals. So, our WWVB receiver is about to receive that signals. These signals can be used in the radio-controlled clocks to synchronize or correct the US times. So, we do not need to retrieve the time online through Wi-Fi.
And as you can see here, the analog input signal is modulated in PWM format. And our analog front end is responsible to remove the carrier that is present in the signal, amplify the signal, and deliver a digital signal, a PWM signal to our digital parts. As you can see here, the signal is done in a modulating duty cycle. For the 80% high duty cycle, it will be corresponding to a 0 bit. The 50% duty cycle high would be corresponding to a 1 bit. And then the 20% the duty cycle high is corresponding to a marker bit. And all of these will be sent into the digital parts.
So after the process of the analog front end, the digital part will get the PWM signal. The digital system will distinguish it as 0, 1, and a marker. The system will store 0 and 1 bits into a register file. Since we do not have enough pinouts on the pad frame, we implement a serial output method to send out the information bits to the off-chip microcontroller to do the further decoding to present in a readable format.
Okay, this is the block diagrams for our analog front end. You can see here, this is our off-chip antenna, which you can see later on our PCB board. After the off-chip antenna, we have our low-noise amplifier. The low-noise amplifier can amplify the input signals without inducing too much noise. After the low-noise amplifier, we have our off-chip crystal filter. The quality factor of the off-chip crystal filter is very high, more than 40,000. And this crystal filter is more like a bandpass filter. It can filter out all the signals lies in the frequencies out of 60K. Because of the high quality factor and its nonlinear behavior, it is very hard for us to simulate it in the cadence. After the crystal filter, we have our buffer. The input impedance of our buffer is 50K, so it can be a load for the off-chip crystal filter according to the data sheet of it. After the buffer, we have our programmable gain amplifier. We have 10 levels of it, and each level is about 10 dB. It is controlled by our off-chip microcontroller, and we have some AGC algorithms for it to control the different gains or the different levels according to our input signals. After we further amplify the input signals, we have the envelope detector. It can filter out the high frequency components, just leave the peak value, or we can call it the envelope of our input signals. With the peak values, we can go through to our threshold detector, which is like a 1-bit ADC. We used Smith trigger to do this, which you can see later when we talk about our schematics. The threshold detector can give us the high value, which is the VDD, and the low value, which are our ground, according to our input signals. So after we have the high and low values, we can give it these values to our digital part. But before it goes into our digital part, we have a very simple level shifter. This is because the signals in our analog part is 2.5 volt, but the digital VDD is about 1 volt. So we have to convert the 2.5 volt signals into 1 volt signals, and then we can give everything to digital decoder. Okay, that's all about our analog front end.
Hi, I'm Zuri Li, and I will start to talk about the digital part for our chip. This picture is a screenshot of the final chip layout in Cadence Virtuoso. Please look at the lower right corner of this picture. The digital part has the system module, which is the decoder, and the SPI module. We did the RTL implementations to achieve the functionality and used the Cadence genus and inverse to generate the layout. We now take a look at the digital block diagram. First, we implement a glitch removal, which can remove the glitches that the analog part cannot process. Then, the signal without any glitches will be sent to the sampler, which is a counter. Because of the PWM nature of the signal, the beginning and the end of a symbol needs to be determined. The flag finite state machine detects the negative edge of the input signal, indicating the beginning of a symbol, and detects the positive edge to start counting. The sampler will count how many clock cycles of the signal staying high, and the sampler will reset to 0 when the signal switches from high to low. The sampling and the digital system clock frequency are both 10 kHz. The decoder block identifies the symbol from the sampler output by comparing the thresholds among 0, 1, and marker. The store finite state machine will monitor the decoder output to see when the two consecutive markers appear. If you see the format frame here on top right, two consecutive markers indicate the start of a new minute. The register file is a place to hold all the zeros and 1 bits. This register file will be written only when the store finite state machine allows it. Once all the bits have been sampled and stored, a signal called micro-enable will be sent to the off-chip microcontroller, enabling SPI communication. Error detection method is also implemented on-chip. This is done by tracking the marker's quantity and position within the frame. These two validation bits are also sent to the microcontroller after micro-enable is put high. As we mentioned before, the digital part has the system module and the SPI module. When the register file has been filled up with 53 information bits, there is no way to do a parallel output to the off-chip microcontroller since we do not have enough pinouts on the pad frame. Consequently, we implement a SPI module to do the serial output. When the register file has been filled up, the system will send out a signal called micro-enable to the microcontroller. The microcontroller detects the micro-enable and recognizes that the data is ready. Then it initiates the SPI data exchange by pulling the chip select line low. The idle state of the clock line is low. The clock starts toggling after the chip select is low. The SPI data is read on the positive edge of the clock and shifted on the negative edge.
Okay, so now I would like to go over our PCB, and as you can see, the board is powered using the USB cable here. The signal will be fed into our ferrite rod antenna. This wire is for coupling programmed signal so that we can use it for error detection tests. After signals coming in, there is this cap here is a tuning cap to make it to the 60K. And then there is some kind of DC biasing here happening here. Then this signal will go into the chip. After the LNA, there will be a crystal filter here, and then this is the variable capacitor here. And all of these potentiometers, like here, these are for current biases. A lot of these small devices you see here are the voltage references for all of the amplifiers, such as the LNA, PGAs, and buffer amplifiers, and also these are all the voltage references. And then after all of this signal chain, and then you can see here there's an R4 and the C19. These are the big RCs for the envelope detector. And then as you can see, you have all of those test points here so that you can use it for probing. After all of this signal chain, this analog output will become digital input into the chip. This one is implemented using a jumper, so that if we want to just only test the digital part, we can just feed in a signal here by removing the jumper, and then just feed in the digital signal instead of using the analog signal that we have in the front end. All of these are the jumper pins, header pins only for like ground connection, so that you can put your probe ground pin connected to these, just for convenience. And then all of these three are the level shifters, that is for interfacing between the chip and the microcontroller. These three are 1 volts to 3.3 volts devices. This little thing right here is the clock generator. It's a programmable oscillator. And then this jumper 7 is just for like in case this doesn't work, we can externally provide a clock in, but fortunately this works, so we don't have to do that. This jumper can just always be here. And then these two ICs here are the also another translator from 3.3 volts to 2.5 volts, because for the AGC devices, the variable gain is achieved by switching on and off the transmission gates, which are 2.5 devices. That's why you need 2.5 volts instead of 1 volts, like these digital signals. Here's a button here for as we demonstrated before, this is for starting the synchronization. And the power comes from the microcontroller board. The USB power will give us 3.3 volts here and the 5 volts here, which the 3.3 volts will be down converted to 2.5 volts via an LDO here. And the 5 volts will go through a buck first, which is around here, and then go through an LDO to down convert to 1 volts digital VDD voltage. And these are the connections. These are the connections of the AGC bits. These going through the level translator to the microcontroller, and then there are some digital signals that will be fed directly into the microcontroller, and then there's one wire that's coming out. These are the envelope detector output and the VComp from the microcontroller. These two are just, we can probe the PGA output and the digital output for, just for demonstration purposes. On the board, we have an LED, I think in here. That's just to show the signal that we receive in case you don't have an access to the oscilloscope. And down here we have an LCD module that is for displaying the output on an LCD instead of maybe looking on the PC.
Okay, let me talk something about our AGC algorithms. So why do we need our AGC algorithm? The first reason is that our input signal strength is different at different locations or even at different time. So we need to adjust our level of our PGA to adjust the gain of our receiver according to different scenarios. The second reason is that our threshold detector also needs a different value of the comparison voltage for different occasions. So how did we do these AGC algorithms? We measure the maximum voltage and the minimum voltage here at the output of the envelope detector for different periods of time. In our case, it's 2 seconds. And initially, we set the 0 AGC level, and when the maximum voltage minus the minimum voltage of the envelope detector out is not big enough, we increase the AGC level gain. So after the AGC level is fixed, we can assign a proper value of the comparison voltage to our threshold detector, so it can give us a very good high and low value, which we can send the data to our digital part. Okay, sounds good. Let's go through to our schematics and some of the simulations. You can see here, this is our antenna. We use the Lambda model to build this. We have some inductors, we have some capacitors. We also have a voltage controlled current source here to mimic the antenna behavior. This is the simulation of our antenna here. You can see the bandwidth is about 120 Hz. So the quality factor is about 50. The insertion loss is 60 dB. This AC simulation is not exactly our antenna behaves when we test our whole chip, but it can give us a basic sense of how the antenna will behave and how the AC simulation of the antenna looks like. After the antenna, we have the LNA. We used cascade topology to build our low noise amplifier. This is because we want to suppress the CGD, the gate drain capacitance here. If we do not have the cascade stage, the CGD will go through to a Miller effect, and it will add back to our capacitor at the antenna, and it will shift the center frequency of the antenna. This is what we do not like. So after we add a cascade stage here, the CGD can be suppressed, and also we can increase the inverse isolation. We use the GM over ID method to build this. The core devices of the NA has a GM over ID about 10, and the tail current is about 500 microamp. It's a little bit big current because we want to suppress the noise of the LNA. So the GM, the transconductance of the core transistors should be bigger. So the current, the bias current should be bigger. You can see here, this is the simulation of our LNA. We run it over PVT, and you can see the gain is about 20 dB to 617 dB. Okay, this is our schematic for our OTA. We use 2 stages to build our OTA, and we use Miller compensation to increase our phase margin. And you can see here, this is the Miller capacitor, and we use a resistor here to move the 0. We also use the GM over ID method. The core devices here have a GM over ID about 10, and the current is about 50 microamp. Because for the OTA, we do not care about the noise, so we want to suppress the power consumption, so we decrease the current goes through it. We also have some dummy devices for our OTA. You can see here, this is the simulation, AC simulation for our loop gain of our OTA. If we connect it with the unity gain feedback, you can see the phase margin is about 60 degrees. But if we connect it to about 20 dB, which is exact the situation in our buffer, the phase margin is 88 degrees. So it can be much better. Let me introduce our crystal filter. You can see here, this is the crystal filter schematic, and this is a decap. The reason why we want to use decap is here. If we do not have a decap, we will have a second peak here. This is because the parallel capacitor in the crystal filter. So when we add a decap, this second peak can be removed. So the performance of the crystal filter is better. Okay, this is our programmable gain amplifier. You can see here we have 3 stages. And for the stage 1, we have 4 levels. For the stage 2, we have 3 levels. And for the stage 3, we also have 3 levels. The levels of our PGA is controlled by 10 transmission gates. We can close or open the transmission gates to control the resistors here. we use the T feedback network for our PGA instead of a simple R feedback network because we want smaller resistors. For example, if the input resistor of the PGA is 50K and we have 40 dB gain, the resistor here is about 5 mega ohm, which is very big and take a lot of place in our layout. So we use T feedback network to decrease the resistance values and decrease the place it took in the layout. This is the simulation of it, and like every 1 second we increase the AGC level by 1, and you can see like after 1 second it will increase, but I do not zoom in, so you will not see the values. But like after like 7 seconds, you can see the level actually increases every 1 second. So this is the simulation of our PGA.
And then now we move on to the envelope detector. For normal rectifying circuit, you will have a diode here, and then you have like a resistor here, and then a capacitor here. But the disadvantage of that is you will require a forward voltage that's going across the diode, which is around 0. something 7 or 8 volts. So basically, if you have 1.5 volts input, what you see at the output is only 0.8 volts, which is not good for our application. In this case, we will have an op-amp in feedback, so that this tries to make this node as close as possible to this node, and the forward voltage will be provided from the VDD. So that solves it, and then this output buffer is to buffer this output signal here. And from the simulation, as you can see that the input signal goes up, the output also follows. And then when input is below the output, this will try to remain the same value because of the very large RC here. And as you can see, it keeps going on and going on. This output will stabilize around this point. The next block is the threshold detector, which is basically a Smith trigger, an op-amp in the positive feedback. The R1 over R0 here is 25, and when we do a simulation, the Vref is 1.55 volts. We have a V threshold high and a V threshold low, 1.6, around 1.6 and 1.5 volts here. And if you go to the simulation, as you can see, the hysteresis plot here, that basically matches what we saw before. And now we finish all the schematics. I want to talk about briefly on the layouts. This is the layout in A. This big chunk here is the input differential pair, and it's matched using interdigitated layouts to reduce some cross horizontal variation. And then these are the resistors for an LA. These two ones are the cascode devices. This is the tail currents, and then there's also the biasing on the sides. And this is the OTA. This is the OTA that we have. This is the input differential pair devices. They have cascodes on the sides. Then these bottoms are the tail currents. And then these are the PMOS devices, and they also have interdigitated layouts and dummies on the sides. This big white block here is the capacitor for Miller composition, and this is the OTA output here. And this is the overview of the PGA. As you can see, you can clearly see these are the three OTAs that we have. For the AVG supplies, we will have M5 on a higher level, and then goes down, and then AVDD here, AGND, sorry. And then all of these are transmission gates that you use for controlling the AGC. There's 4 here. There will be 3 here and 3 here. That corresponds to 10 AGC levels. And then these are resistors that's coming along as we shown before on the schematic. And this is the envelope detector. Again, this is one of the OTAs, and then this is another OTA here. And this one is the P diode 25 device that we saw before. This is a diode here. And then threshold detector. This is just one OTA with 2 resistors in positive feedback, which is one of this and one of this.
The digital part is achieved by RTL implementations of each block. We use the Cadence genus and the Innovus to generate the layout, and then port back to Cadence Virtuoso to integrate with the analog part. We use the reports provided by Innovus to do the static timing analysis and the power analysis. The first one is the system module decoder. It is 108 times 108 micrometers. As we can see, the thin gray wires at the top left are the parallel decoder output. The few wires on the top right are the digital control signals. The second one is the SPI module. It is 100 times 100 micrometers. The thin gray wires at the bottom are used to get the outputs from the decoder, and the three wires at the top are SPI signals.
Okay, you can see here, this is our test setup for our chip. I gave it an AM modulated signal. The carrier frequency is 60 kilohertz. You can see here, the AM frequency is 1 hertz, and the amplitude I give it is 3.5 millivolt. And you can see here on our oscilloscope, the yellow trace is our input. It's about 3.5 millivolt, and this is our input. You can see here. Also on the oscilloscope, this is the pink trace here is our low noise amplifier out. And you can see here the yellow line is connected to the low noise amplifier out pin, and the gain is about 70.8 dB. And let me change the time scale. You can see the LNA can amplify the signal correctly according to the AM modulated signal. After the LNA, let's test our buffer. Okay, you can see the amplitude after the buffer is much bigger than the LNA because the buffer we designed has a 20 dB gain, but the crystal filter has a like 10 dB loss, so the amplitude is not like 10 times the signal after the LNA. But you can also see there are some bounce on the maximum value of the buffer out. This is because our crystal filter is not exactly centered at 60 kilohertz. It's about 59.9996 kilohertz. So the nonlinearity will cause the bounce you found here. Okay, after buffer, let's test our programmable gain amplifier. Okay, you can see because this time we did not give any AGC level to it, which means the AGC level is 0, the gain is 1, so you can see the amplitude is very close to the buffer output. And then later when we test our AGC algorithms, you can see we can assign different AGC levels to our PGA. The PGA can amplify the signal further. After our PGA, let's test our envelope detector. Okay, you can see the yellow, pink trace is our envelope detector out. You can see the envelope detect can give us the envelope of our input signals correctly. The falling edge is much larger than the rising edge because the large RC constant of our envelope detector. Okay, the last one is our PGA out, is our threshold detector out. You can see for this time the value is always 1 because our comparison value is given by our off-chip microcontroller controlled by our PC, but this time we do not test our AGC level, so we just assign a random number to our threshold detector, so this value is always high, and later when we test the AGC algorithms, you will see it can change according to different comparative value.
Okay, for this test, we are trying to see how the AGC works. In this time, we're going to use a real signal here, which is a phone. The phone will act as a transmitter. Even though that our circuit works at a 60 kilohertz frequency, the coil that is in our phone here is actually capable of driving up to a frequency of 20 kilohertz. And this works by having the third harmonic of the signal sent to the antenna and all of the other frequencies will be filtered out by both the antenna and the crystal filter. So that's how this this setup will be working. And for right now on our oscilloscope, the yellow trace that we have is the PGA output, and our AGC level will start out at the minimum level, so no gain. And as you can see, there's nothing coming out of the scope because the gain is actually just super small. And then for the pink trace, it's going to be the digital signal that we wanted to show on the previous section. But this time, since we have algorithm in place, written code in the microcontroller, this time we will be able to see the digital signal coming up. So if I press this button here, the synchronization should be able to start. But before that, I'm going to say this is done by measuring the maximum and minimum value of the PGA output. We can briefly showcase it here. I'll press the button here. Now it should start, and as you can see, the gain starts to increase. And the reason that it keeps going up is because the maximum and minimum value does not meet a certain threshold, our desired value. So it'll keep increasing like this. And then the comparator voltage for determining the high and lows of this waveform will keep being updated. And should be the stability. This means that the loop is being stabilized. And as you can see, the gain doesn't increase anymore, and you can get a digital signal here. And you can clearly see that all of the symbols, for example, this is the 80% high, which corresponds to 0. And then this is the marker. These are two markers. That means the beginning of a minute. And then you can see here and also here you have a half duty cycle, which means the 1. So basically the AGC loop changes the amplitude from very minimum to an acceptable value, and then determines a good comparator voltage that is between this upper value and the lower value. For our digital parts and error detection tests, we will use Python to write arbitrary waveform into the keysight waveform generator. As you can see, the arbitrary waveform has already loaded here. And then we will use a frequency of 60 kHz here, and then amplitude is 1 millivolt peak to peak. And then now we will turn on the outputs. And this is not measuring anything for now. We will run a test. So for the test case for this is from the document called the Enhanced WWVB format. It's supposed to be at July the 5th, 2012. And then it's 5:30 p.m. UTC. And what we modified is to add an extra marker at the leap year bit. So what we should be able to see is that it tells us an invalid result and then a non-leap year, even though it's a 2012, it should be a leap year. So now it's being on, and then if I press this button here, and then I'll wait for the result to come. Okay, and as you can see here, because we made some corrections in the microcontroller code, this doesn't show the UTC time but the New York time, but the values of them should be correct. It's just the leap year is now non-leap year even though the year is 2012. And obviously you can see here it's calling invalid because there's an extra marker in our input signal. What we can do is measure some of the pins of the validation bits. I think TP31 and the TP33 are the validation bits. If I probe at this node here, it has nothing here, which means the marker validation is not correct. And also if I probe this one here, and Yeah, and then also the shifting validation is also not correct because it's also 0. If they are both valid, they should all be 1. And the microcontroller will read these bits as valid if they're all at 1.
Okay, that's all about our WWVB receiver. We would like to thank you, Professor Peter Kingett, for this opportunity and his support and guidance throughout this course. We also want to thank you, Apple Incorporated, for the sponsorship for the chip fabrication. We also would like to thank you, Hongzi, Moore, Alfred, Ray Xu, for all the guidance and support on design, capital flow, and feedback. Thank you all.
Thank you all.
Thank you all.